Thank you, everyone. So we are from QuantCo, and we are going to discuss a bit on how we see and how we proceed on trying to bridge the gap between moving from an analytics environment to a production one, which probably for most of you might have some experience on that. So I'm Ignacio, he's Nick. Both of us are software engineers at QuantCo. We are a data science-oriented company where we help our clients to solve challenging problems, and one of them is actually going to production. For a bit of context, in general, in these clients and in the type of work, tends to be highly complex because there is regulatory issues, business requirements, and technology constraints that you can imagine in big corporations and in, for example, highly regulated environments like insurances. So, raise your hand who goes to deployment writing some Python code like this. For whom this is kind of what they deploy. Yes, so sometimes this is enough. I mean, we have a very simple fast API application here where we load a model and then basically we expose an endpoint and we just get a payload that the payload has to look like what the model is expecting. We have to load it in pandas and then we do a predict on this model with this data frame. However, as I said, in our line of business, this is usually not enough and you need more complexity. You need more because you need more things to take care of. For example, what happens if you want to have more than one model being hosted at the same time in your service? Or what happens if you have different models and these models need to be there for a long time and they have different environments trained? And when you have different environments that they are trained in, maybe when you put a model trained 5 years ago or even 1 month ago into a new one, you don't get reproduction of your outcomes. Let's say in insurance, you want to have reproduction of prices up to the cent. And if you change, let's say, your MKL version of your fast mathematical library, and then you get, let's say, 2 cents off, that's not good. But you still want to have them all together in the same deployment. Even more, you can have different models and you can say, well, I could have them in different endpoints, and with that you can say, well, I can deploy them in different containers, fine, but what happens if you want actually to put them in one single endpoint with a common schema and actually not separate in different containers because, let's say, technology constraints, cost constraints, whatever. And even more, you want to give them some configuration when you deploy them. And that configuration, it's not necessarily via code, so then we start adding complexity and complexity and complexity. And furthermore, in cases, for example, where data science, it's closer to business than IT, we as, let's say, data engineers or the people in operations that we are trying to put machine learning models into production, we would like to have more flexibility, more control over what is happening in the application. So for us, when we talk about bridging this gap between analytics and production, for us, it means basically taming the complexity that rises when all of these different elements are considered. And we are going to focus mainly on these 3 topics. One is about interfaces and contracts, how they can help us in diminishing complexity or managing this complexity, how to lean into automation, and third is focusing on how to try to bring work from after you decide to deploy something to work being done before the deployment. And with that, I leave you with Nick to explain about the interfaces and contracts.
Exactly. So also a warm welcome from my end. Happy to have you all here. When we look into interfaces, there are several approaches how you can view interfaces and how you can make use of them. And in the next slides, we're going to dive into how we can use these interfaces in order to handle the complexity of several IT systems communicating, teams collaborating, on interfaces, and also how we're going to handle multiple models in there. So let's split, or let's view a technical interface or interfaces from different directions. The most intuitive approach is basically to see an interface as a technical implementation. For example, an external API schema that's called by the upstream service that calls us. Then you could also have an interface for the model that abstracts away all the feature engineering and modeling logic behind it. These are technical interfaces that you need in order to run your system. But at the same time, these technical interfaces can also be seen out of an organizational perspective. For example, the model interface could be the interface between the modeling team or data science team and the engineering team. And the same also holds for the external interface, where you basically have the intersection between the engineering team of a specific service and some other IT system. So we're going to look into how we can use these interfaces in order to tame the complexity that Ignacio has just shown. In order to make this a bit more tangible, let's start with an example. So on the left, you can see the example we've just looked into, and on the right, we can see a payload. So let's assume we are in the area of e-commerce. We built an algorithm that basically can predict the price for a product based on some customer attributes. Here in this case, we have an ID for a customer, a name, an age, a category, a preference category, a price sensitivity, and maybe some experimental group. So this example is totally made up. No guarantee here that every attribute that is required is actually there. But in this case, with the flat payload, we can directly plug it into the model, and let's hope that the attribute names match the names that the model expects, and everything is fine. But usually in the web native world, you don't really have a flat payload, and names probably also won't match up. So in order to actually get this to the model, we need a mapping. So on the left, you can see this nested, human-readable, web-native payload. And this also represents the external API schema of our web service. And let's just call this, or let's just take this as the operational world on the left. In order to bring this to the analytical world, where the actual inference happens, we need to do a translation. This can be a flattening, it can be a renaming, but it can also be adding some values, like for example, the experimental group here. And this already is a first step of decoupling. So we're now able, with having this translation in place between the two interfaces, to at least a bit more independently work on the streams. As long as we have this translation in the middle, the engineering can more freely work on the external interface and the analytical team behind the model interface. If we now just have one model deployed, maybe having this translation in place doesn't seem to add so much benefit. You might not directly see the gain we get by this. For that reason, let us look into an example of how much flexibility this actually brings us. So for our example of the e-commerce store, let's assume we want to do some A/B testing. So we want, based on certain rules, give different clients different results and evaluate how good our model performs. We could, for example, do this by an upstream service calling our web service, and within the payload we have the model name that we actually want to use. That could be model A or model B, and then our API service routes based on this model name to a certain model. So far, so good. The complexity in this case is that you have several IT systems involved in it. And as soon as this is the case, you need to migrate interfaces, change them, extend them, and you're a lot slower in fastly setting up experiments. So it would be pretty nice to kind of get rid of this. And as a first step, what we can do is, for example, in this mapping that we've just shown, add the logic of inferring where we want to route the traffic to. So in this case now, we just take the overall payload of the upstream service. We don't need the model name anymore, but we could, based on some logic, if we want to do some random mapping, we could just use a modulo on the ID, or maybe there's some, from a business perspective, more sensible way of splitting the groups. We can then infer with the function which model we want to route to. So this would be the case of adding this model name to the model interface and then calling the specific model. It's nice now within the team of operating the web service, we can tweak things, test things quite fastly without managing the external schema or without changing it. But we can be even smarter in this case. So here we see the example. Let's assume the different models that we've deployed that represent the experiment only differ by a factor of a scaling. In this case, there's no need to actually deploy several models. We could just extract the scaling factor into our mapping function and now compute based on a key the certain factor that should be applied, put into the model. So yeah, this is basically, it doesn't really change now a lot in the external interface anymore, but this also helps us then to get a lower footprint of our application. And I think just by having this translation in place, you already have seen what freedom it gives us to design our architecture. So now let's take a step back. What we've been looking into, let's term it a bit better now, is the service interface. So it's external, it's public, it's hierarchical and nested. It has proper names that is agreed upon between several IT systems, usually, and it is maintained by engineers. So that means here it's entirely the task and also the freedom of the engineering team to take care of extending it, scheduling migrations with other upstream IT services. And then we have the model interface, which is the internal schema. It's private in terms of being within this web service. It's flat. It translated into the data science world, let's say, and it might have odd names. What do we mean by this? So sometimes you get extracts somewhere, they might be in German with column names, then you translate them to English, then the model has English input names, and they start to diverge from actually the names that is the common agreement between systems. So there also mapping is needed. And then this model interface, and this is one key aspect, even though it's just a tiny mentioned here on the slide, is the shared responsibility of this interface. So how we do this in our team is it is mainly under maintenance of the engineers, but the data science team contributes to this. And this is basically how we make sure that we collaborate jointly on this, and this is our common understanding of how this model interface should look like. So having shared responsibility sounds something like overhead and extra communication and extra effort. And in this case, it adds friction. But in general, you mainly want to remove friction to make things more efficient. But here we explicitly want to add it in order to gain speed afterwards. Because if we have a common understanding about this interface and how we extend it, we can make sure that later on, when we want to deploy things, that the models comply to a certain schema. And that we early on, for example, add attributes to the schema, which of course can evolve, but it shouldn't be like changing every time entirely. So this is kind of a common ground for engineering and data science to extend this. And one thing, where Ignacio will talk a bit more later about, one thing how you can make very early on sure that things don't start to diverge is as soon as the modeling team pushes some model somewhere into registry or Git or wherever you version your models, you could run CI checks to pull this currently built or currently valid model interface or a branch of this model interface that should be released with the next release and directly check if things align. Then you don't need to later on, in a short time, extend your external interface to get new values, but you have a good view on what you need to change in order to get the next model deployed. So let's take a step back and just review what we've seen. So we think the benefits of having the split and this translation between the two worlds gives us a lot of flexibility and speed. It allows these interfaces to independently evolve. We add friction exactly at the place where we want it to have a common understanding of how we translate from operational world into the analytical world, and therefore we can go faster and smoother to production. Obviously, it has the overhead of developing and maintaining these mapping for maybe versioned interfaces as we add or remove attributes from our external schema. So with this, I would hand over to my colleague.
Yes, so after we saw now about contracts and interfaces, I'm going to talk about workflows. And when we think about workflows, we can see them in two dimensions. The first dimension is the degree of automation that a workflow or particular tasks in a workflow can have, that they can go from something very manual to something completely automated. The other dimension or degree of freedom that you can have in a workflow is, I call it relative execution time, which means basically when this task or part of a workflow executed from the point of view of when you decide to go to production, when you decide to deploy. So there is a very particular time point where you said, hey, I want to deploy, and that defines before and after of a process. So, of course, if we have these two dimensions, we can do the obvious thing to plot them on a plane, and then you have 4 quadrants, which probably for anyone that does product management, operation staff, it's very familiar. And the idea is that we would like to get away as much as possible from the lowest right corner, meaning we want to get out from a place where things are being done manually, because that includes more errors, it's cumbersome, it's slow, and we want to get away from things being decided or being performed after the decision to go to production. Of course, it's impossible to get rid of all of that, but at least we can try to basically do the following, move away from it. Before I continue with this workflow part, I want to discuss something very key on how we think about workflows, which is what we call a model ledger. Basically, a model ledger is a table, in a way. It's a definition, primarily and hopefully append-only, that defines, in our case, when a model is being active. So we are even going a step further. We are not only, when we deploy a model, we also specify when that model will be active. And that gives us also flexibility on deciding, oh, well, we are going to deploy now, despite that our models are not going to be active until a week from now. But it gives us some flexibility on deciding, and again, it's a decoupling of the decision to deploy something and the decision of when is this active. So this model, usually, it's valuable for tracking changes. If you are in a highly regulated environment, it might be a way of being controlled and audited. So usually, it might be a good idea. And it has to be human readable. So it's a way for us to convey what we want to do. And this basically triggers a lot of the automation to decide, what we want to deploy, when, and configure applications. So that's why, what is this ledger for? It specifies when a model is active, provides a way to configure. Like Nick told you, we want to, for example, certain people from in certain conditions that they were defined for the experimental groups, we want to give them different scalings. Or maybe we want to give them a discount. You don't know. And this also helps us to avoid a lot of recomputations for each deployment. So this is something how basically a model ledger could look like. In our case, it's a set of rows where there is a start and ending. In this example, basically, we are covering the month of February 2022. And it says, well, we have 3 groups. We configured 3 groups. 1, 2, 3, and all of them, they have a factor of scaling 1, and basically we are saying, and sending them to models A, B, C. And that means basically the model has all the logic on what to do with them. Let's say you want to provide different prices if you are in an e-commerce for whatever reason, depending on these experimental groups. But then, let's say now, after the 14th of February, it's already after Valentine's Day, you decide to give everyone a discount of like 10% discount, and you send them to a new model, which is the Model D. So here you can convey and you can keep track, and in a human readable way, to communicate basically for product owners how you're going to production. And the whole point is that we have to build automation around this definition to then actually produce the deployment artifacts that we want. Let's say configuration, build, like packaging, and building models that can be very broad, and the generation of images if you're deploying something like in a Kubernetes environment or something that it's a container orchestration. Now, the situation usually, as I said, in our context, we have some time like pain points, and probably you also have them. So the process usually it's very time consuming, is error prone. There is a lot of recomputations happening for each deployment, and a lot of this can be solved by trying to automate or trying to work ahead of the deployment point in time. And as I said early on why this very simple Python service, it's not cutting it, is because we want many models, we want them to be all together. So yeah. And here we can see mapped into these 4 quadrants a lot of different tasks that basically would be involved in one of these processes of going to production. And we see that it's heavily towards being defined after the point of time that deciding to go to production, and also highly manual. In this case, this manual means manual execution of certain scripts, but still it's quite manual. And it's error prone, it's slow. Then if we try to work our way out, and basically we made a strong effort on trying to improve our situation in one example, we managed to move most of the things out of the second quadrant. Sadly, we couldn't move a lot of these things to the 4th quadrant in the top left, which would be before deployment, decision, and automated. But at least now we have a really one single action, which is the actual deployment, that it's fully manual and it's decided after, and it's done after the decision to go to production. And basically now it's much nicer for operations. The result of doing this change for us is that it improved the reliability of our deployments, reduced the time to deploy. We were spending like 8 hours in one single deployment, and we managed to reduce it to 2. And now basically we enable a product owner or a business owner to basically be able to drive this deployment, and you don't need an engineer anymore. So this leads to less issues at deployment time, deployments more frequently, and freed engineering resources. Now, we didn't only stop there, and this is kind of a shameless plug here a bit. This is not the end of the story. We have invested even more on this, and to make deployments simpler and easier for us, and we are going down the route of using Onyx. So if you are really interested in Onyx and how it can help you in simplifying deployments, I recommend you to look at these 2 talks that colleagues of mine have done previous years, particularly the one of the left, that it's more operational, whereas the right one, it's more on the side of how to use tooling that we have created to actually represent machine learning components in Onyx, in the Onyx ecosystem. So, to finish and wrap it up, lean on automation. Lean on trying to work ahead of the deployment decision and to prepare work before you want to deploy, because then you can catch problems before you want to deploy, and it's less firefighting, less stress, and all the good stuff. Use interfaces as a way to convey how you want to communicate. And last is, as Nick said, sometimes friction is useful, and use it. And with that, we're done. Thank you for your attention, and now we have some time for questions.
Thank you, Ignacio. Thank you, Nick, for your presentation. Yeah, we have some questions. The first one is, we have models which wins a lot from request batching techniques. Do you have any idea how it might be implemented?
In our case, usually we are not working with batch because we get single requests. Now, if you want to batch them because your model performs much better and you have the time to be able to do that, because for us it's a constraint, we cannot take too much time to answer. We have certain timing constraints there. You can basically accumulate them and then send them to your model. Then you have to play with how much you can wait. That's difficult to say upfront without knowing your business case.
And might be the interface you shown, might it also contain some parameters for such kind of batching?
I mean, of course, you can do whatever you want in your interface, and if your interface, you said, well, instead of a single payload, instead of having one single payload defined here, you can say, well, actually, what you have, it's a list of or a collection of these requests in a single time, and then you have to process them on your service. Of course, you can do that, and being batch or not doesn't change the fact that you have a decoupling between an internal representation on how the models should behave from how you receive data from external upstream callers.
Good, thank you. Which role plays testing when putting models into production? Do you have any tips for test methods or maybe tools?
No, we struggle with that too, sadly. We are still learning there and making mistakes and trying to do it better, but we don't have a recipe there yet, sorry.
But you show a way how to deploy multiple models at the same time with this interface. Might it be utilized to maybe route a part of traffic right after the deployment to test if it works and roll it back other way around?
I mean, of course, you should be having some sort of staging area where you do testing, and that's kind of a no-brainer. But a more sophisticated approach or a systematic approach on how to do testing in a better way, as I said, we also struggle, and we have used many different ways because we really have to reproduce certain results from analytics and production up to the cent. So we struggle with that too.
Okay, good. Let's hope our community and our developments somehow will find a way how to not struggle from this problem. Okay, and we are done. Thank you, guys.
Thank you.